to welcome today's speaker, Daniel Wigdor, who graduated from here actually in 2008, and since, I guess, spent time first at Harvard as a fellow, is now working at Microsoft as a usability experience architect. There's also an affiliated faculty member at the University of Washington's Department of Computer Science and Engineering and School of Information. Dan is a former member of the DGP group here, and today he's going to be talking about architecting next generation user interfaces. And just a quick process description. He's going to give the talk until noon. We'll pause and let everyone leave if they need to run somewhere, and then we'll have about a 10-minute Q&A section after that. Okay, so great.
Thank you very much, Kai. Are my levels okay? Can you hear me in the back? Excellent. So it's very exciting to be back at the University of Toronto. Thank you very much for this opportunity. What I want to talk to you about today is next generation user interfaces and the vision that I've had for these and how it has changed over the time that I've been working at Microsoft and having the exciting opportunity to apply some of the research that we've been generating in the HCI community to actually building some of the tools and products that are emerging. So when I stand at the front of the room and you're watching me and I'm communicating with you, you're hearing the words that I'm saying, but you're also seeing my body language, you're seeing my posture, and there's this very rich flow of information that is coming from me to you. And of course, I'm also getting a similarly rich flow from you back to me. Computer systems that we all interact with on a regular basis have a greatly reduced flow of information. We can think of this as a deficiency of bandwidth, where the amount of information that the human is able to input into the system is limited to left, left, up, down, and click, and a little bit of text entry, of course, too. Now, it should be said that the user interfaces that have been designed to take advantage of this information flow are highly refined and have gone through more than 40 years of iterative design, and they're incredibly powerful and suit their purposes very well. This is the Xerox Star, which is one of the first WIMP, Windows icons, menus, and pointers-based graphical user interfaces. And clearly, it's a great success of design and engineering. Now, the opportunity that we have today is that there is a plethora of new technologies that are enabling us to have a much richer user experience. And the particular group that I have dedicated myself to over the last several years at Mitsubishi and at Harvard and now at Microsoft is the domain of touch-based user interfaces. And what excites me about touch-based user interfaces is that they have the potential to increase the bandwidth of communication from the human into the computer. Now, touch in particular is interesting because the technologies that enable it are now becoming commercially available and less expensive. And so it's an opportunity for us to bring some of the research out into the world and to start to build these and to build tools that people can interact with on a very large scale. So we can think of the activity that I'm going to be talking to you about as attempting to increase this flow of information between one source and another, to see if we can get past this sort of experience now that the computer has when it's listening to its user. And in fact, it's even a little bit worse than this picture suggests. Not only are we communicating across this line, but the set of instructions that we're allowed to pass is rather small. Now, what I want to do is to look at how can we bring all of the knowledge that we have as computer scientists and system builders to creating these experiences. And there are 5 pieces that we need to leverage in order to take advantage of this opportunity that we have now with these technologies. The first level is in building new sensing devices and in processing for the data streams. And so, for example, Microsoft Surface, a product that I have been using to do a lot of my research recently, is a triumph not only of sensing, but also of computer vision. This is a layer that we need to do in order to get to this enriched flow. And this, along with the next step, which is defining the input language, the mechanism by which the human will send information into the machine using this larger communication channel, these 2 steps have been the focus of the research community in HCI in particular over the last several years. And of course, these are necessary first steps. But what I'm interested in is in solving a set of problems that have started to emerge because this work has been done and we're able to understand its limitations. It's not just the case that we need devices that can understand the human and that there are mechanisms by which the humans can send signals into those devices, we need also a mechanism by which the user can understand how to send those signals into the system. So the graphical user interface, for example, the user uses a mouse and clicks around on the screen. Without the on-screen affordances, the buttons and the sliders for them to click on, they wouldn't be able to have their user experiences. And we think of this as the affordance language that we offer to the human. Now, the next piece that is especially important with new technologies is the need for a feedback language. As we move beyond pushing buttons to send information into the computer, the physical feedback that the user normally has from that mechanism is taken away, and so we need to replace that with another feedback language. Now, what's interesting about this model, and what is a little intimidating to me talking to a lot of theoreticians in this room, is that it does contradict Alan Turing's vision for how humans and computers would interact with each other. Turing believed that eventually we would reach a symmetry of communication where the human and the computer would interact with each other in the same language. This vision is different than that, and it's different for an important reason, and we'll look at it in more detail in the rest of the talk. The final step, of course, is understanding where these technologies, where these languages can be used to allow users to do things that they couldn't do without these tools, and to build systems that leverage them to enable the person to do, the user to do those things. The focus of this talk is going to be on the affordance and the feedback languages in particular, and I'd be happy to talk about my work in those three other areas in more detail during the Q&A. First, let me convince you that this is an opportunity. So this device we see in the bottom left here is the Diamond Touch from Mitsubishi Electric Research Labs. It's a piece of technology that allows multiple users to interact with a system simultaneously. And when it was first built, the software toolkit that was built for it is the Diamond Spin toolkit that we see in the top right, which is essentially a mouse-based interface that has been adapted to allow users to interact with their finger instead of with a mouse. This is a perfectly valid vision to say that these new technologies don't require new interfaces, but what I want to prove to you now is that if we were to build different interfaces, we could leverage the capabilities of these technologies and what they afford for the human better and build better experiences. So here's how I proved it to myself. I and a partner designed a user study where we asked the question, can a user take better advantage of the increased bandwidth when they're using a direct touch interface? So this is a classic experiment that's been done since the mid-50s in the Air Force by a man named Fitz. You present the participant with a place where their cursor starts on the screen. They move their cursor and click on the green box. They drag that box into the dock. So they select the box, then they drag it. We had the participants perform this several times with two different devices. One was a mouse-based interface where they saw the cursor. The other was a direct touch interface. Now, not surprisingly, the difference in performance between those two input devices was negligible. But if we ask the question, how could we design the interface differently to take better advantage of the capabilities of the technology, we will start to see a difference. And here's how we modified this classic experiment. Now, instead of just grabbing the green rectangle and moving it to the box, now the user must also resize that rectangle and move it into the box at the same time. The way that they do this is they have two cursors that are either controlled by two mice or by two fingers with a direct touch interface. And now we start to see an opportunity where the human, the user, can be sending a lot of information to the system at the same time to simultaneously move and resize that dragged object. Now the bandwidth, of course, of these two input devices was the same, or at least what the computer was receiving of it. All they were doing was moving 2 points of control. But when we look at the results, when the users were interacting with the direct touch interface, the touch table, here the vertical axis is time, we see they're able to perform this task significantly faster with the direct touch system than with the mouse. So what this tells us is that we can go from this sort of one-handed interface to a two-handed interface. Now, of course, when you're interacting today, you're not resizing boxes, right? But what the purpose of this experiment was to demonstrate that if we want to allow a higher bandwidth communication, a direct touch interface mirrors better the fundamental human capabilities, and so we can take advantage of it better. So this is a first indication of this opportunity. So now, being a bit of a convert, I turned my attention to, well, what is the language by which humans will give their input into the system? Now, a lot of other work has been done in this area, and I'm going to share with you a problem that I had to solve recently and what our solution was to it and how it led to the realization that we needed an affordance language. So, who here has seen Microsoft Surface either in a commercial or on the web somewhere? Excellent. So what you know about Microsoft Surface is that it's a big table and you can put 2 fingers on it, and if you go like this, the pictures get bigger, right? So if we wanted to expand on that capability just a little bit and try to make a complete window manager, where instead of just being able to move things from one place to another and make them bigger, instead we wanted to allow the user to scroll and zoom within the window, we thought that we could do that just by making little tweaks to that very simple language that is so approachable and so understandable. The way we did it was this. We asked the question, what are the natural gestures? What will users do if they walk up to a system without prompting? And we asked them to perform this task. And the way that we did this experiment was we showed users, participants in the experiment, before pictures and after pictures of what the interface should look like, and then asked them to perform the gesture that they thought would lead to that change. So this wasn't actually an interactive system. We were just interested to see what their physical action was. So let's do the experiment together. Here's the before image. You've got a web browser window down at the bottom of your screen, a very vertical screen. And here's the after image. The browser window is now at the top of the screen. What gesture would you do to get from the before to after? Wow. Dave. All right, so this is where we separate the smart Alex from the non-smart Alex. So what we were interested in is what was the gesture that most people would perform, and universally, with actually 100% agreement, we saw participants put 1 finger down on the device and slide it up. They say, that's how I want to move things. Fair enough, it's direct manipulation, it makes sense. What about this next question? What are the natural gestures? Here's the before. So now the thing is already at the top of the screen. Here's the after. We've scrolled a little bit in the window. What gesture would you do to scroll inside of a window with a direct touch? So I see a lot of 1 fingers, and I see a lot of 2 fingers, and the 2-finger people are the Mac users, I would imagine. But of course, you as computer scientists recognize right away the conflict. If you show the participants this first, they'll say they want to use 1 finger to move, to scroll, and if you show them the other one first, they'll say they want to use 1 finger to move. And what was surprising was if you separate it just by 1 other trial, the participants won't even notice the conflict in the gesture language. They'll just do the same gesture twice and expect, well, the system will just know that I want it to scroll. So what this tells us is that we have to design something. We can't rely on what users will guess. So what do? Well, I decided, well, let's, rip off Mac. So what do the Apple folks do? Well, 1 finger usually moves the cursor around the screen. We're going to promote that to moving the whole window. So if you grab something with 1 finger, you'll move the whole window. If you put 2 fingers down in close proximity to each other, you're indicating you want to scroll or zoom within the content. So I'll just quickly take you through that gesture language. So looking first at how to move whole windows around. Of course, it was, as we just saw before, we have the window on the screen. A user puts a finger on it, slides their finger, and the window follows. And of course, because this is multi-touch, we can also resize with 2 fingers like that. Now, to the content, we can do the in-content operations using 2 fingers. So when we want to scroll, we put 2 fingers down in close proximity to each other, and we slide. And so we're scrolling sideways in this case. And if we want to zoom, we put down a 2nd pair of fingers and slide them apart. Okay? So it's a very simple rule that we're trying to get our participants to guess. And in fact, because we borrowed it, did I say rip off? Borrowed. We borrowed it from one of the leaders in the field. We thought, well, there'll be a lot of experience people can bring to bear on this. And in fact, we did ask people whether they were Apple users or not when we performed the experiment to see how well this works. So the question we now ask is, this rule is so simple, can we rely on users to guess this difference? So we brought people into the lab, and what you see here is a pair of participants. These are 2 guys who know each other. And we bring in 2 people so that they'll talk to each other and so we can hear what they're thinking. And here we see the person running the experiment holding up a piece of paper, and now we're showing them, here's the before, here's the after. Now perform the gesture in the system to get it to transition between those two states. So I'm going to take off my mic here so we can hear the audio. Can you hear it? All right, well, we can't hear it very well, so I'll tell you what's happening. You maybe can tell from their facial expressions. They're trying to guess what's happening. And we see one participant who starts off, he just puts his hand down, and he discovers that if he mashes the whole thing with his hand, he can get it to scroll. And the task that he's performing is to scroll the window. And so the conclusion that he comes to, what this pair of users come to believe, is that the way that you scroll is by mashing the whole device with your whole hand. And that belief persists across the life of the experiment. At the end, when we ask them to explain the gesture language to someone who they think is a non-experimenter, that it turns out is one of our confederates, the way they explain it is that, well, you have to mash it with your whole hand. Here's the next one. This is a father and daughter pair. And what we see here is the father is experimenting with it, and he's sort of decided that he might be able to pin it down. And so he tells his daughter to reach in and admonishes her for drinking at the same time. And now we see the way that they perform the gesture, and the conclusion that this pair come to is that the way you scroll a window on this system is you hold it down with two hands. Right? This, of course, is what we came to call the giving a cat a pill interface for multi-touch interaction. So what this told us was, even these very simple rules, people won't guess. And so we need to provide a mechanism that will induce this behavior. And what we're trying to get to is people interact with these devices in this very high bandwidth way. And so we're interacting with multiple fingers and gestures all at the same time. We need a mechanism to tell the users how to do it. And so that's why I became particularly interested in developing an affordance language for how to induce that behavior. Now, we're not the first people to try to come up with a method to teach people gestures for a gestural interface. Who is familiar with this? Quite a few. So anyone who had a Palm Pilot back in the mid-90s has seen this before. And so Palm had the graffiti language we see at the top for entering text, which looks something like the alphabet, and this was a gestural interface you did with a pen. But when we got into the more abstract actions, like I want to execute a shortcut, that we see at the top of this column, it's this sort of squiggly pigtail gesture, which is of course, completely unguessable. And so what this is a decal that would ship in the box with your Palm Pilot. And you would, your first action, your out-of-the-box experience is to take this decal and adhere it to the back of your new $500 piece of electronics. And so whenever you need to know how to perform the gesture, you just flip it over and look at the gesture language. Now, I think that we can do better than this. If for no other reason than the particular device we were using to do this research was a Microsoft Surface. Anyone who's seen one knows they weigh about 300 pounds. And so asking the users to turn it upside down is not a reasonable method. So what do we do? Well, what we endeavored to do was to build an affordance language that spanned all touch gestures. We didn't want to build an affordance language that would work only for a particular subset of gestures. So we surveyed the field of all input technologies, all sensing technologies that are used now to create touch input, and understood what are the things that they can sense. And we built a taxonomy of all possible gestures that could be performed by a user to give input to those devices, irrespective of the particular gesture languages they happen to use at this moment. So here's how we built our taxonomy. First, you have to understand the stages of the gesture, and I'll walk you through that as we're going along. So you all have seen Microsoft Surface before, I now know, and so you're familiar with the put two fingers on it and stretch apart gesture. And so the steps of that gesture are, at the beginning, you're out of range and the fingers aren't seen by the device. And then you put your fingers down on the device. At that moment, when you touch the device, you've registered the mode. And you've informed the system that this is the gesture I'm going to be performing. That's the registration phase. At that phase, in the common denominator hardware that spanned all of the available sensors, there are 4 different possible mechanisms that the user could have used. They could put down one finger or the tip of a pen. They could put down multiple fingers. They could put down a shape of some kind with their hands or multiple shapes. Next, the user continues the gesture, and they either change the shape of their posture or they don't, and we call this the continuation pose. So in the case of the 2 fingers to stretch, there is no change in the posture. You don't have to add another finger to the device or change the shape of your hands. But so it's either static or dynamic. Then the user enters movement into the system to specify the value of the parameter. This is the movement phase, and movement either follows a path or it doesn't. And in the spreading apart case, there is movement, there is a path. So this gives us a taxonomy that's 4 by 2 by 2. And it gave us a space that we could work in so that if we could build a teaching mechanism that could teach this space, we believed it could be generalized to teach any gesture that used these types of devices.
Can I ask a question?
Sure.
So, I mean, is this supposed to be complete? What about velocity or force or pressure or?
Right. So so the question was, I haven't mentioned things like force, velocity, pressure, hovering above the table, and so on. So the way that we constructed the model was to create a theoretical lowest common denominator piece of hardware that spanned the commercial and research devices. And so while some of those can sense pressure, for example, most of them can't. And so we started with this smaller set in the belief that we could grow it to niche cases. And to the point of velocity, that's a function of the movement. And so we would use graphics to explain to the user that velocity is a factor in performing this gesture. So it certainly is the case that there are specialized hardware or specialized gestures that this may not cover, but we hoped that this would provide enough coverage that we could then grow out from there. So if we do the full combinatorics of this 4 by 2 by 2, we get this space. And we populated this space with gestures from the literature where available or made up new ones where they didn't exist. And I'll show you now very quickly video so that you can get a sense of what those gestures were, even though I suspect you won't be able to follow or memorize all of them, thus perhaps proving the point we have to teach them to you. So here we see all of the gestures that populate that taxonomy. Do you think you could guess all of those without help? The jazz hands gesture gets a lot of. Okay, so there's our gesture. So what do we now do with this? Well, we have a taxonomy that defines the space of multi-touch gestures. We now also have a sample gesture language that we've contributed to the community so that other teaching systems can use this and teach against it to allow comparison. But now, of course, we're interested in developing our affordance language to teach this set of gestures that could then be generalized. The way that was done was using a mechanism that we call user shadows. Is Dustin here right now? There he is. So Dustin came and did an internship with us at Microsoft, and so he did a lot of the implementation and building of these ideas. So the shadow, the user shadow system, oh yes, and you see the Canadian engineer ring on his finger there. So the idea behind user shadows is that we give the user feedback about what they're doing at this moment. So their raw input is being echoed after it's been through a few steps of computer vision, so that we can then annotate that and provide directions for how to manipulate the shadow, so that the user can understand exactly which of their movements actually have an effect on the sensors, starting to get rid of some of that superstitious behavior that we saw in the earlier example. So how do we do it? Well, you'll recall that the first step in performing a gesture, here I'll transfix by Dustin's hand here. Recall the first step in performing a gesture is for the user to know how their hand has to land on the device. And so the mechanism that we use for that is what we call the registration pose guide. And the registration pose guide lists gestures and the different hand poses that the user needs to have in order to perform that gesture. Now you'll notice that the names we pick for these gestures are intentionally arbitrary, because we wanted this gesture set to be free of the semantics of a particular application. We didn't want the name to help the user to remember what the gesture was. So we picked these arbitrary names. So if we zoom in on one of these cells, we show the participant or the user of this system two things. We show them here's what the shape of your hand should be when you hit the device. And we also show them here's what the user shadow should show you when you're performing this gesture correctly. Right? So how does that translate? Well, here is one particular gesture which we called cat. And here's how it works. The user has to put down one hand, slide to the right, and add another finger. See it again? So they're touching with their index finger, sliding to the right, and adding a middle finger and coming down. Now, of course, this gesture is intentionally arbitrary because we're trying to cover the space. All right, so we need to teach that gesture. So the first thing that happens is that the user sees the registration pose guide on the screen. This could be integrated into a toolbar or other UI mechanism. And they can see what the name of the function is that they want to execute, and so they know how to land their hand on the device. Next, you can see to the left, we've added annotations to the user shadow to show them what action they need to perform in order to complete the gesture. Because in this case, putting one finger down on the device allows them to perform any of the ant, cat, or bee gestures. So from those, and of course in a real UI that might say cut, copy, and paste or something else, but again, free of semantics intentionally. So the user can then select from among them by performing the gesture. So here's how the annotation works. The user knows that they want to perform cat. They follow the lines that guide their movement. And you'll see a circle get added to tell them to put down another finger, and so on. And so this gesture teaching system takes care of the problem of registering the correct posture in the first place, and over time the users get faster and faster and able to perform it. How well did it work? So this shows the results of an experiment that worked as follows. We brought participants into our lab, and we had them perform all of the 15 gestures of the set, and we had them perform them each 8 times, so 8 by 15. And all the way through, they were guided by the help system if they wanted to use it. On the last block, without telling them that this would happen, we took away the help system. And then we measured how well they could remember the gesture. Now, as the basis for comparison, because there wasn't already a mechanism to teach these multi-finger gestures, we also created a system that used videos, where a user in advance records how to perform the gestures in video, and the person running the experiment can call up that video to see how it works. So we compare our system against a video teaching system. Here we see 2 different results. The first is, in their first attempt, in that last block where they didn't get help, were they able to perform the gesture correctly? And we see that, in this case, many more of the gestures were able to perform correctly if they were using the shadow guides to learn than if they were using the video system to learn. If they didn't succeed on their first attempt, we allowed them to keep trying until they got it right, and we took a measurement again as to how many of them they were able to perform correctly by the 4th attempt, and still the shadow guide system was able to provide better help.
Confidence intervals there overlap.
Yes.
Isn't that contradictory? Doesn't that mean that there is no statistical difference?
Well, let's dive into the stats at the end so that I don't get derailed, but yes. Yeah.
So do I understand correctly that video was participant is just looking at how it's done, and shadow guide is he's doing it with guidance?
Well, the way that it worked was the participant would watch a video and then they had to perform the gesture.
I see.
Right. So it wasn't just that they watched the video 7 times and then were tested.
I see.
Okay. So let's take a look at what we then did with that result. So we found that this was promising, we got good feedback, and as you point out, the confidence intervals suggested to us that this mechanism showed potential, but was not the end result that we needed. So what we did was we continued to iterate. So if we look back now to the original gesture language that we were trying to teach our participants, this difference between moving the whole window or moving the content with 2 fingers, and applying some of the lessons of shadow guides, we iterated on the design and took away the piece where we made sure that the teaching system was free of the semantics of the application, and instead integrated it into the application. And that led to a system that we call just-in-time Chrome. So here we see a user performing the usual gestures that they're able to do with the multi-touch system. We see this Chrome come up that shows them how to resize the window by grabbing the handles. And now we also see something similar to the registration pose guide, showing them that if they use 2 fingers, they can scroll and zoom. And in a moment, you'll see the user take advantage of that advice and do some scrolling by putting 2 fingers down. The zoom icon tells them that if they were to grab that with another finger, they would be able to zoom. So we use the shadow guide's experience to give us the knowledge that if we were to provide the users with mechanisms that they could follow, they'd be able to learn the gestures quickly. We iterated to produce this design. This design ultimately is the version that is going to be shipping in a commercial product. But it also showed much more promise in the research sense as well. Now, having provided a mechanism to teach people gestures, we also need to provide a mechanism to give people feedback in how the system understands their actions. And here to give you some intuition is why. So picture yourself in a situation where you reach up, you touch something that you believe is a control, and it doesn't respond. Like that. When you bring people into a lab and you give them this situation and you give them a mouse-based interface, and you ask them why didn't the control respond as you expected, they offer three possible explanations. They believe the control was disabled, or they believe the control just didn't do what they thought it would, or they think that the software has crashed. If you give someone exactly the same user interface and ask them to perform it instead of with a mouse, with their finger, they touch it and it doesn't work, what do you think they do? What would you do? Push harder, push more, push again. And in fact, the realization that this was necessary came to me partially out of my experience in the research world, but also sitting on the tarmac at JFK with a touch-based interface in the back of my seat and a teenager who didn't know his own strength poking me in the back of the head for 3 hours. So you could think, Newton had the apple. Next time I'll go with the fruit. So what this tells us is that we need a feedback mechanism to tell the user, here's why it's not working. In the case of the tarmac, the reason the user was pressing really hard on the screen was that whenever the captain would make an announcement to say, yes, we are going to be here longer, the touch interface would stop working, and the music would turn off. And this person was trying to turn the volume back up. In fact, this is such a problem now that when you fly, flight attendants will often announce, please don't push too hard on the screen because there's someone else's head on the other side of it. So looking at the mechanism that we saw with shadow guides, where we echo raw input, this gives us some of the feedback, but it doesn't give us everything that we need. This tells the user, yes, we are registering your touch, but it doesn't solve all the problems I'm going to take you through now. There are 6 sources of error that we need to solve with feedback. The first is what we call activation action. Different hardware devices have different responses with touch. So in this case, because it's a vision-based system, sometimes it activates before the user actually touches the screen. With resistive-based systems, sometimes you have to push really hard in order for it to work correctly. We need to provide the feedback to understand that source of error. The next is accidental activation, where a user will intend to use one control but accidentally touch something else. In this case, the only consequence is that they're moving something from one place to another, but we've also seen the case where that modifies a control. The next problem is disabled content, and that was the case that I showed the video of a moment ago, where in this case, the play button that the user is pushing doesn't work until they drop an album into the music player. Right? But of course, you can understand other circumstances where the controls might be disabled. Next is the fat finger problem. So here you'll see sometimes the users are successful in touching those objects and sometimes they're not. They are, in all cases, successfully physically touching the object, but the system doesn't see them as having touched it. And the reason for that, for those of you who haven't played with touch before, is that the user, is actually touching with this rather large pad of the finger, but only one point is used to do hit testing. This allows you to have nice high-precision interfaces so that you can have pixel-accurate selection, but it also means that the user can't always understand why they weren't successfully touching objects. Next is the problem of manipulation constraints. Here the developer has decided that this window should only get so big, and the user is trying to get past that constraint. And the last is the over-capture problem. This is the special case where the user is trying to grow and they've over-constrained an affine transform that doesn't allow skew. And so in this case, their finger slides off the object. And so it's not direct touch anymore. It doesn't keep the right pixels under the right place. Overcapture also has another special case that I'll show you in a moment. Now the consequence of all of this, of course, is that participants and users of our systems get frustrated. Or they start bashing on the back of your seat on the airplane. So the approach that we took was to understand all of these problems and to build a large matrix of solutions to all of the problems. But of course, when you're providing a user with feedback, especially when it's not primary task feedback, you want it to be subtle. You want it to be as subtle as the mouse pointer, and that it can disappear out of consciousness when they're not paying attention to it and provide enough feedback when they are paying attention to it. And so the first step that we took was to reduce a rather large state machine to this state machine. And I'm not going to walk you through all the states. But what this does provide us is, if we had a visualization that covered all of these states of touch input, to give you some intuition, 0 is when the user first puts their finger down on the device, and then all of the different possible error causes that can result after that. If we could come up with a visualization that covered all of these cases, we would have a visualization that solved all of the problems that I showed you a moment ago. Now, the nice thing about working with a product group for the last couple of years is that instead of the look that research systems typically have, this had 6 months of iterative design by professional designers. And so we arrive at this set of visualizations that goes by the affectionate name No Touch Left Behind. So the goal of No Touch Left Behind, or NTLB, is that we provide the user with enough information that can resolve all of those errors. Now, I won't take you through all of the errors and their solutions, but do understand that there are different states of this visualization. It's not just sparkles coming out of the finger, but it is specialized sparkles that do particular things. So first, how do we solve the fat finger problem? So recall the fat finger problem, of course, is this issue that the system reduces hit testing to a single point from the large area. What we do is that we try to educate our users about that fact. So we're not actually helping the user to be more precise in any one selection, but rather we're teaching them how to be more precise in the future. So here the user misses, when they lift up their finger, see how the visualization very subtly shrinks away. The point that it shrinks away to is the point that's used for hit testing. So the last thing the participant sees is this point that they need to care about. And I'll demonstrate to you why that's important in a moment. The next is how we demonstrate constraints on resizing. So in this case, you'll recall the window can only get so large, but now we provide feedback that says, yes, I see that your finger is trying to make it larger, but I'm not going to let it get larger. And last is a particular case of the over-capture problem, which is where one user reaches over and takes capture of a button that prevents another user from using it. So here you'll see that particular case. So we see the user showing us how this button works. Now another user of the system is going to capture that button, and now it won't work anymore because that finger has captured it. But now we provide information that allows social protocols to mitigate that circumstance. Now, of course, we could change the capture model to eliminate that case, but this capture model works better in more circumstances. Now, to the point of fat fingers, we performed an experiment where we asked participants to make selections of targets and then measured the performance whether they were using our visualization or not. In this case, the vertical axis is errors, and with the feedback for small targets in particular, that's target size in pixels, we see that the users are able to learn very quickly where that point is, and they can become more precise when they have this feedback. And this mirrors feedback that we've seen in the wild now that this has been deployed commercially. The other point that we were trying to accomplish is that the users will have an increased understanding of what's happening in the system, so that we'll eliminate those superstitious behaviors that we saw before. The way that we studied this was we put 2 tables in the room, 2 surface tables that were running the system. We brought the participants in and allowed them to use each of those for several minutes, and then we asked them, what do you think the difference is between these tables? The only difference was one had No Touch Left Behind running and one did not. Many of our participants believed that there actually was a difference in sensing. They thought that the tables were better, the one running No Touch Left Behind actually had improved sensing and vision systems. But in truth, all we were doing was changing the visualizations. And of course, some participants also picked up on all of the states, the visuals in particular, and understood that it was giving them more information. So the consequence of all of this is that when we have No Touch Left Behind running on a system, participants and users of our technologies are much happier. And what's particularly exciting about this, of course, is that this is a research contribution. It was published at ACM West, but also this was actually deployed in the wild. We went through and built this system, and so now we're getting reports back of its success in the wild as well. Now the last point in our in my 5 pillars approach is to talk about the research and building of tools. Now, a great deal of my work at Harvard University was focused on this particular point, and I'm going to give you the quick version. So, building specific tools that leverage these systems is important. It's not the case, at least in my case, that I believe that touch is going to replace the desktop and the mouse. The desktop computer and the mouse are highly iterated. They serve their purposes really well. What I'm interested in is understanding when we build these systems as well as they can be built, can they enable people to do things that they couldn't do using existing tools? To answer that question, I embedded myself with a group of astrophysicists for 6 months at Harvard University. And I used ethnographic techniques that come to us from anthropology. But essentially, I lived among them and was taught to be an astrophysicist. And by the end, I was told I was the dumbest astrophysicist in the group. But considering it was a Harvard astrophysicist, I didn't take that as an insult. So, I learned about what it was that these users were doing with their data. The tools that they were using were preventing them from doing their research well. And they were preventing them from doing it quickly, and it was preventing them from doing it collaboratively. And I'll give you a taste of how they do their work. So here's the output from the Spitzer Space Telescope, which is just as expensive as Hubble, but you probably haven't heard of it because it senses in the infrared band and so doesn't produce pretty pictures that make nice press releases. But they use the infrared band to look for their phenomena. What they often do is they'll perform statistical and mathematical processes on this data and then compare visual output. They all work visually. And the mechanism that they use in order to compare those differences is that they'll look at the visual under one process, and they'll look at the same segment of sky under another process. And just to quickly prove to you that this is the same segment of sky, look at this area here where the arrow is pointing. How they do their comparison is they do this deep analysis using tools that they build themselves. They then take the output, load it into PowerPoint, and do this. So it's clear that there's a deficiency of the tools that they're using. When I first started my work, it seemed like the output of the process was going to be just building tools that they'd be running on their desktop. But what emerged was that they believed, and it turned out to be true, that using large multi-touch and other services like what ended up being built. Here we see a large high-resolution wall at the front of the room and a multi-touch table where the users sit to do their research. By doing this, we enabled them to do their work collaboratively. And one of the great gratifying outputs of this process was when I got to the evaluation phase, I asked them to not just come and give us feedback on the system, but instead come as a group with current research and do research as a group using the tool. And in the very first 2-hour session, by using our tool, they were able to find a new result that resulted in a new submission for telescope time that resulted in new science. And the feedback that we got from them was this was enabled because they were able to do their research collaboratively, and they were able to do their research collaboratively because of our tool. And after a lot of begging, we found a way to leave them with a version that they could continue to use. So I hope what I've demonstrated is that this opportunity is real, and this particular 5-pillar approach to research is a good mechanism to realize that opportunity. And in particular, these 3 less serviced elements of it that have emerged out of my experience at Merle, at the University of Toronto, at Harvard, and now at Microsoft will give us some new and interesting results. In the future, how I'll continue to do this work is to iterate on touch computing to continue to solve these problems. In particular, I've already begun collaborations with several institutions to build new and different affordance and feedback languages to try to improve that result from shadow guides and other systems. That really is the Georgia Tech logo, I think. I searched for it for a really long time, and I couldn't find a coat of arms. Huh? It is. Oh, right. Thank you. Should have just asked you instead of spending all that time in the first place. So, in addition to iterating on the feedback and affordance languages with collaborators at these institutions, continuing to build particular tools to find applications for these technologies is the opportunity that we have as researchers, and the opportunity that I hope to avail myself of with partners at the University of Surrey at Microsoft, and recently at the Seattle Lighthouse for the Blind. Continuing past touch interfaces Taking this 5-pronged approach to other user interface technologies will allow us to realize their potential. And in particular, this approach now has framed a lot of the work to try to iterate on and improve pen-based and tablet computing in the commercial group at Microsoft and the Windows team. Now, in addition to the work that I've shown you in this presentation, I should also point out some of the other work that I've had a hand in doing. Building multi-surface systems in particular was the topic of my thesis work. The area of applied psychology allows me to apply techniques that we learn from our colleagues in psychology departments to understand effects such as superstitious behavior so that we can properly find solutions to the problems that come up in the research. Volumetric displays and other projects were done here at the University of Toronto. And this is a very rare version of this picture. When we submitted the paper for reviewing, one of the reviewers told us that it looked like a Buddha rubbing his belly. And so my collaborator, Toby Grossman, is usually posing in that shot. And also my mobile phone text entry work here done at the University of Toronto. And I think maybe there are some of you who are participants in those 8-hour-long experiments. And I thank you for still hanging into research. And I would like, of course, to thank all of the people who have contributed to this work from Merle, Harvard, the Microsoft, the product team, and Microsoft Research. And thank you very much for your time, and I'd be happy to take your questions. So how I was told it would work is that those of you who have to leave now can, of course, and we can stay and take questions for 10 minutes. Okay. Dave.
In the examples you showed us, the experimental work with subjects, there's a certain commonality among your subjects. Have you investigated the issue of cultural differences?
Yeah, it's a great question. So the question here was about cultural differences in recruiting subjects and teaching them things like gesture languages. Actually, cultural differences is one of the big challenges, not only in learning differences, but also in defining gestures. So I'll ask, for example, this is maybe the wrong way to ask this, but does anyone find this offensive? Okay. We have a group at Microsoft who is dedicated to researching things that are problems in other cultures. And so this particular gesture, they couldn't tell me, they'd lost the source material to tell me where this was offensive, and I haven't been able to find it. But for example, this.
Greece.
It is Greece. Oh, great. Excellent. My host is offended. Should have done a little bit more research on that one. So yes, there are certainly cultural differences in defining these interfaces in the first place, especially because of the semiotic issues. And in the teaching mechanisms that we need to use, the first system that I demonstrated had an intentional divorcing of the semantics of the gesture and the mechanics of the gesture. And cultural issues and experience is how you can start to blend back together the semantics and the mechanics. So for example, using gestures where we have people move things from one place to another so far seems to be a universal effect. But particular gestures might map better onto things that are culturally relevant. So the answer is we've thought about it, but we've been limited by our resources and so haven't studied it yet. Other questions? Oh, sorry. I'll take your.
Yeah, what about surfaces that give you feedback, like heat and texture and surface geometry,
Yeah.
whatever? How does that work?
Yes. So the question is about other mechanisms for providing feedback. So here, with touchscreens that exist now, we just have a hard physical or a flat surface. So what if we could somehow deform the surface or do other things to provide the feedback? We would still need to design that feedback language, but adding the haptics as a tool, as an arrow in our quiver to do that design would be useful. And in fact, one of the mechanisms that I'm looking at to do that is one of the pieces of hardware that I've developed. I didn't focus at all on system building in this talk, but one of the pieces is a touchscreen where you hold it in your hands and touch the device from the back. And it's in that mechanism that I've started to investigate putting lattices and other things to induce behaviors. And also for the Lighthouse for the Blind, I've modified the surface with my team to have a lattice work with home indicators, like the physical tabs on the home row, to help guide their input. So it shows promise. I think once the technology is available to do these sorts of things in real time, then we can start to leverage it. Other questions here?
So, in any of your experiments, you show aggregate results about how across the user population that you study, how well they can do with this type of feedback, this interface, and so on. Did you find any, let's say, user categories where some will do better with certain interfaces, certain types of interface, certain types of feedback, others would perform better using, for instance, other types of feedback, and you could start to adapt to user?
Sure, yeah. So the question is about what about individual differences between participants, since what I'm reporting here is aggregate results. And of course, one of the limitations of trying to fit this much work into a small talk is having to sort of concentrate on those pieces. Individual differences happen with gestural in this sort of interface, particularly with age. And so young people are able to pick up gesture languages much more quickly than older participants. And we have different hypotheses as to whether this is just that they have a lot of experience with other interfaces and therefore have that interference or other such things. So that's one such mechanism. Gender also plays a role in some of the interfaces. So there are these categories of users. Adapting the interface to the user is definitely something that's on the roadmap. I think some of the danger of doing that is that when the user is learning, they need to have a target that they're learning towards. And if that becomes a moving target because they're simultaneously trying to adapt to each other, it can create problems in learning. And that's some of the difficulty that some of the adaptive systems work has seen over the years. But it'd be interesting to see how we can overcome that with feedback to show them how it's adapting and to allow them to use it better. Other questions? Kai?
It seems that one of the goals of your work is to eliminate the possibility of superstitious gestures that people use with the system.
Right.
But why do that, especially if the superstitious gestures are natural to the users and also effective in that they work?
Yeah. So the question is, it seemed like I was focusing in my talk on eliminating superstitious behaviors. But if that works, why don't you just allow the superstitious behavior to continue? And we're getting into potential metaphysical arguments, and I'll just sort of set that aside from the conversation. So the problem with superstitious behavior is that if it doesn't properly align with what the system is expecting, the participant will start to exhibit behaviors, or the user will start to exhibit behaviors that are orthogonal to the goal, right? So in Skinner's original work that defined how superstitious behavior happens with operant conditioning, where there was a pigeon in a cage and the pigeon could get food pellets by hitting the paddle and the food would come out, and they would learn that association. Superstitious behavior came when Skinner took away the button or made it just disconnect from the mechanism and instead put the food on a timer. And now the pigeon would start to believe that whatever it happened to do at that moment before the food came out is what caused the food to come out. And so you get these elaborate dances that the pigeons would start to perform. And potentially this is a circus act, right? So maybe there's nothing wrong with it. But what we see in applying that learning from experimental psychology to what's happening with our users is that a user will start to believe things like pressure matters. And so when they are trying to perform a gesture, they'll be applying pressure to the system, which might actually, in that particular case, the point that's used for hit testing is calculated geometrically from the contact area. When the user applies pressure, the contact area changes, and so that point jumps. And so the user will never get to what we call expert behavior, where they can predict reliably where that thing will happen. So it's really just about making sure the user understands what their actions are that will evoke a consequence and being able to improve and get to that expert status.
There are no other questions. Let's thank the speaker.